This video will cover a solution guide to problem 34 from chapter 5. Block A weighs 45 newtons and block B weighs 25 newtons. Once block B is set into downward motion, it descends at a constant speed. Calculate the coefficient of kinetic friction between block A and the tabletop. A cat, also of weight 45 newtons, falls asleep on top of block A. If block B is now set into downward motion, what is its acceleration, magnitude, and direction? The strategy here is to start with a free body diagram of each block in the system. From those, we will be able to write down the force equations for each block in the x and y directions. We will then be able to manipulate those equations to solve for the unknowns we are being asked to find. Let's start with part A. First, we will draw the free body diagrams. Block A has 4 forces acting on it: the force of gravity pulling it down, the normal force from the table pushing it up, the force from the tension of the string connecting block A to block B, and the force of friction resisting the block's motion. Block B only has 2 forces acting on it: gravity and the force of the connecting string pulling the block up. From Newton's second law, we know that the total forces acting on an object is equal to the mass times the acceleration of that object. So next we want to write Newton's second law equations for each block in both the x and y directions. In this problem, I will designate that the positive x direction is to the right and the positive y direction is upward for both blocks. This is something that is flexible in solving the problem, and different people will have different preferences for the coordinate system. The important thing is that you define your coordinates early and stay consistent with your choice throughout the entire problem. So with the coordinates chosen, block A has 2 forces acting on it in the x direction: tension and friction. Tension is pulling the block to the right, which was defined as positive, and friction is pulling the block to the left, which was defined as negative. This means the tension minus the force of friction will be the net force in the x direction. And so, using Newton's second law is equal to the mass of block A multiplied by its acceleration. Block A also has 2 forces acting on it in the y direction: gravity and the normal force. Gravity is pulling the block down, while the normal force is pushing the block up. So the net force in the y direction for A will be the normal force minus the weight of block A. Since the block is not moving at all in the y direction, we know that there will be 0 acceleration. Therefore, we can set the net force in the y direction of block A to 0. Block B has no forces acting on it in the x direction, and we therefore end up with a trivial equation of 0 equals 0. In the y direction, the block has 2 forces acting on it: tension and its weight. Tension will be pulling the block upward, while the force of gravity will pull the block back down towards the ground. This gives us that the tension minus the block's weight is equal to the mass of the block multiplied by its acceleration. Keeping the goal of part A in mind, we need to figure out how we can use these 3 equations we just derived to find an expression for the coefficient of kinetic friction. Since we already extracted the equations we need from the free body diagrams, let's get those out of the way to make some room. In the problem statement, it tells us that block B will descend at a constant speed. This tells us that B's acceleration is 0. Because block B is connected to block A, the magnitude of the accelerations will both be 0. We have the definition of the force of friction being the coefficient of kinetic friction multiplied by the normal force of what it is acting on, which in this case is block A. But we were not given the value of the normal force, so how will we find it? If you look at the y equation for block A, we have that the normal force of A is equal to the weight of A. Okay, so now let's look at the x equation for block A. Since acceleration is 0, it tells us that the force of tension is equal to the force of friction, or the coefficient of kinetic friction multiplied by the normal force of A. Now looking at the y equation for block B, we see that we can also say that the force of tension is equal to the weight of block B. The force of tension in both of these equations are the same, so what we can do is set the expressions for the tension equal to each other. We have now successfully reduced our 3 equations down to one equation that contains only one unknown, the coefficient of kinetic friction. We could cancel the g's from both sides, but if you look at the problem, it gives us the weights of the blocks, not the masses. So to save some work, we will keep the g's on both sides. Dividing both sides of our equation by the weight of block A, we find that the coefficient of kinetic friction is just the ratio of the weights of the 2 blocks. Subbing in the values from the problem statement, we find that the coefficient of friction is 0.56. Part B adds extra weight onto block A in the form of a sleeping cat. Recall from part A that when block B was set in motion, the acceleration was 0. Adding the cat onto A is going to change our acceleration to a non-zero value. Just thinking about this conceptually, would you expect the acceleration of block B to be upward or downward? Because the acceleration was 0 in the previous part, after block B is set in motion, the extra weight on A is going to slow the system down. Block B will be moving downward, which means if it is in fact slowing down, we would expect the acceleration to be upward. Let's check this. Like the previous part, Because A is connected to B, their accelerations will have equal magnitudes, but opposite signs. If A is accelerating to the right in the positive x direction, B is accelerating down in the negative y direction, according to the coordinate system I have designated for this problem. So we are going to set the acceleration of A equal but opposite to the acceleration of B. Adding a cat to the surface will not change the coefficient of kinetic friction, so we know that mu sub k is equal to 0.56. We also know from the y equation for block A that the normal force is equal to the mass of block A plus the mass of the cat, all times gravity. And the equation for the force of friction is the coefficient of friction multiplied by the normal force. So we have two equations left, the equation for the x direction for block A and the equation for the y direction for block B. And we also have two unknowns, the force of tension and the acceleration. In this particular problem, the force of tension is not asked for, so what we can do is solve one of the remaining equations for tension and plug that expression for Ft into the final equation. It doesn't matter which equation you choose, so let's just start with the equation for block B. If we add block B's weight to both sides, we end up with an expression for the tension in the string. Now let's look at the equation for block A. Subbing in our equation for the tension, our equation for block A becomes the weight of block B minus the mass of B times A minus the force of friction is equal to the mass of block A plus the mass of the cat, all multiplied by the acceleration. We have used all our Newton's second law equations, so let's move those out of the way to make room. If we move the mass of block B multiplied by the acceleration to the other side of the equation and factor the acceleration out, we can divide both sides by the total mass to get the expression for the acceleration. Subbing in mbg for the weight of block B and the expression we found for the force of friction, we now have an equation for the acceleration in terms of variables in which we have the values for. Subbing those values in, we find that A is equal to negative 2.17 meters per second squared. But remember, because of the way I defined A above, this is actually the opposite value for the acceleration of B, meaning that the acceleration of block B is upward at 2.17 meters per second squared, which checks out perfectly with our prediction at the beginning of this part.